Electronic communication is the science of moving information. It is the precise, intentional transfer of data from one point to another, across vast distances, and through environments that are constantly trying to degrade it. It begins with the baseband signal. This is the raw, unconverted electrical waveform that comes directly from a source transducer. When a human voice hits a microphone, the immediate electrical output is your baseband. That raw signal can be analog, forming a continuous wave of time and amplitude, or it can be digital, snapping into discrete, separate values. Regardless of its shape, every electronic communication system follows the same pipeline. The source hands the baseband over to a transmitter, which fires it across a physical channel, like copper wire, optical fiber, or the open air, where it battles distortion and noise until it hits a receiver, which reconstructs the signal for the final destination. How that data flows through the pipeline depends on the system's directionality. A simplex system flows in only one direction. A television broadcast tower can only transmit, and the set in a living room can only receive. Half-duplex systems open up two-way traffic, but they force users to alternate. Two radios can transmit and receive, but never at the same time. The physical channel has to clear before the direction flips. Full duplex systems remove that waiting period. In a telephone network, information travels in both directions simultaneously, requiring infrastructure capable of handling constant, overlapping streams. But drawing a block diagram or assigning directionality rules only maps out our engineering intentions. It does nothing to solve the physical barriers of pushing a raw signal through the air. This brings us to the central bottleneck of wireless transmission. Why can't we simply hook an amplifier to a microphone and broadcast a 3 kHz human voice directly into the atmosphere? The answer lies in the laws of electromagnetics. For an antenna to efficiently launch a signal into space, its physical size must be proportional to the wavelength of the signal. Specifically, it needs to be at least 1/4 of that wave's length. Low frequencies have extremely long wavelengths. For a standard 3 kHz audio signal, a quarter wavelength antenna would have to be roughly 25 kilometers tall. Even if we could construct a tower stretching into the stratosphere, direct baseband transmission introduces a second problem, multiplexing collision. If everyone transmitted raw 3 kHz audio into the air at the same time, every signal would occupy the same physical space. They would interfere with each other, resulting in unreadable noise. To escape the physical constraints of this baseband bottleneck, engineers must manipulate the wave. They need a mathematical technique to reduce the required antenna size and isolate individual signals from one another. That technique is modulation. Modulation is a mathematically precise frequency translation. To see how this translation works, we examine the properties of a high-frequency carrier, usually a simple continuous cosine wave. This spectral plot shows a pure cosine wave through a Fourier transform in the frequency domain. It consists of two distinct impulses at f0 and negative f0. This spectral simplicity reflects a rapid oscillation in the time domain, pushing millions of cycles per second. This behavior allows engineers to exploit the frequency shifting property. The property states that multiplying any signal in the time domain by a complex exponential shifts its entire spectrum in the frequency domain. We apply that theorem to our 3 kHz voice baseband. By multiplying the low-frequency message with our high-frequency carrier wave, we force the fast carrier to conform to the envelope of our slow voice data. In the frequency domain, the baseband spectrum is lifted from 0 and shifted up to the high f0 carrier frequency. Translating the message to a high-frequency band shrinks the transmission antenna from miles to meters. It also creates distinct frequency lanes, allowing thousands of signals to be multiplexed into the sky without collision. To understand the limits of this shift, we must deconstruct the standard amplitude modulation equation. The math yields 3 distinct components: the original carrier wave, an upper sideband, and a lower sideband. This chart maps those outputs onto a frequency spectrum. A central spike representing the carrier is flanked by 2 symmetrical curves representing the upper and lower sidebands. The actual voice data exists only inside those 2 sidebands. The central carrier spike contains no message. To control how much data fits onto the wave, engineers use the modulation index, M. This ratio governs the amplitude of the message against the fixed amplitude of the carrier. When the index is under 1, the envelope is clear but shallow. At exactly 1, modulation is perfect. The data envelope touches the zero axis without breaking. If it exceeds 1, the envelope crosses the zero axis, tangling the waveform and creating severe overlapping distortion. While standard AM effectively solves the antenna problem, pushing the modulation index too far destroys the data envelope. Signal stability requires strict mathematical discipline. While standard AM established global broadcasting, it is highly inefficient in terms of power distribution. This graph shows the power distribution. In a perfectly modulated signal, exactly 2/3 of the total transmission power is spent on the carrier, leaving just 1/3 for the sidebands that actually hold the information. To build long-range systems, engineers had to eliminate the power cost of transmitting the carrier. This led to the first optimization, double sideband suppressed carrier, or DSB-SC. By removing the central carrier before transmission, all available power can be used for the sidebands. Suppressing the carrier saves transmitter power, but the receiver must become far more complex, generating a synchronized reference wave to reconstruct the signal. With the carrier gone, engineers turned to the remaining sidebands. Because the baseband signal produces positive and negative frequencies, the upper and lower sidebands are mathematical mirror images containing the same data. Engineers exploit this redundancy by using single sideband transmission, or SSB. Filtering out one sideband cuts the required signal width on the frequency axis perfectly in half. Single sideband transmission maximizes power while doubling the channels that fit into the spectrum. This efficiency makes it the standard for global point-to-point radio. Slicing a sideband perfectly in half requires incredibly expensive electrical filters at the transmitter. To manage this, engineers use vestigial sideband. By transmitting one full sideband and a tiny remnant of the other, the filtering requirements become much easier and cheaper to manufacture. Vestigial sideband enabled early television broadcasting by balancing the massive bandwidth requirements of analog video against the need for affordable consumer receivers. From the initial baseband problem to single sideband, communication architecture is a continuous engineering negotiation. It is a balancing act between power efficiency, bandwidth conservation, and the physical limits of hardware.